Good afternoon, everybody. So, this is Mohammad Shojafar. I would like to explain, let's call it as a fourth presenter in this workshop. First of all, I would like to thank Professor Conti for his invitation and thank for all of you for attending in this workshop. Well, I just want to highlight that I would like to explain about 4 papers, and due to the time which I have, I try to abstract to discuss of these papers. 3 of these papers coming from the IEEE transaction papers which we published this year, and 1 is the conference. So I just want to explain that I would like to talk about 3 problems. The first problem, as you can see the name, the lifetime aware commodity hardware machine states. I would like to talk more about the commodity hardware, one of the emerging hardware in the recent network environment. And I would like to discuss about the different states and the side effects of the different changing of the state of this commodity hardware, how it could affect on the lifetime of the network, and which criteria or which metrics we can consider in this network to decrease this problem. The second problem, we would like to go toward for the joint solution of inside a cloud data center. We would like to take care and take into account also this transition change, and we would like to take care about 2 problems altogether. The first one is talking about a maintenance cost, the cost which caused by a failure rate over the devices inside this system. And after that, we would like to address the electricity consumption over this cloud data center environment. After that, which is coming from our most recent work, which is that's why it's under review in transaction of network and system management, service management. We would like to talk about a fault-aware service function chaining inside a software-defined networking. After that, we make a conclusion and I give some future direction. And at the end, I would like to ask you a question about your help, let's call it, your suggestions to me to improve my work. So for the first problem, I should say, so I just want to say that a different problem, I give a general scope of the problem and then explain about the results and the solution that we propose in it. With our problem, let's call it our work in all these slides, talk about the green networking. So you know that the green networking is the aim of the exploiting the power, using different power management policies inside the network in order to decrease the energy and electricity consumption of the engaged component inside a network. One of the most important components inside the network is commodity hardware. So what is a commodity hardware? Commodity hardware is the hardware that it used inside the system based on in order to manage the traffic. For example, if we have a huge amount of the traffic in the system, we need to turn on some devices in order to facilitate the process and speed up the task, and in order to respect the quality of the service of the network and avoiding violation of the service level agreement that we have with the users that they request these tasks. Commodity hardware, so as you know, the hardware that's sometimes added into the network in order to facilitate the situation of the network. Commodity hardware use different states. It could be in active mode and it could be in sleep mode. It means like a hibernated in order to use it in the later time by the huge of the traffic coming to the system. This kind of state efficiently manage the power state of the system. So if we use the different transitions over a commodity hardware, it's obvious that we could control the energy consumption and we go toward for providing a green networking. But we should address the big problem and the big issue that recently a lot of network providers are engaging with this type of commodity hardware. The long run or long transition of the commodity hardware, it has some side effect in the network. For example, if we consider the commodity hardware as a server, if we turn on-off server in a long period of time, we lose that kind of server because the server's lifetime has been passed. So the content provider and the cloud center providers, or the to be generalized, for the commodity hardware providers, it's so important for them to use some metrics to manage their system and how this kind of device could be, in the long run, could be transitioned from the active mode to passive mode. One of the, let's call it, in order to go toward details of this kind of problem, we would like to address the first problem as comprised of two sub-problems. The first sub-problem, we would like to think about and discuss about a commodity hardware temperature. So and you can see, we tested in a real test bed, and I can show the slides, the details of the slides in the next slide. We will see that the change in the transition, it counter effect, and it has side effect of the temperature of the system, and it will distribute the temperature heating situation over other component in the network. On the other hand, we go for a generalized case, for a large scale case, and we tested by we tested as a simulation in over an ISP network with a huge amount of commodity hardware inside the system. So let's start by first sub-problem of the problem number one. As you can see, we would like to talk more about the commodity hardware, and we would like to talk about a real measurement on simple test bed we test over a commodity hardware type we address in our solution. In this problem, the commodity hardware that we would like to talk about is a server. So we have one server. This server could be turned on or turned off. And so to be simplified, it could be in the active mode or in the sleep mode. And you will see that by changing the state of the server, the system could produce a lot of heat, and it could be side effect in whole of the network. And you will see that by abrupt stopping of the fan over the CPU and RAM of this kind of server, it could be spread the heat over the components and increase the temperature transient before reaching the steady state. Steady state is when it would like to go to the state that it could be. In the transient case, it increases the heat in the system, and it side effect in the whole of the system, and it causes a failure rate in the system. So the failure rate, it tells us to change that kind of server in the long run. Let's see the test bed. So as I explained before, we use one server as a type of the commodity hardware for our experiment. We use a ID rack interface, which is installed over a commodity hardware installed over a server in order to measure the temperature of the system as of the motherboard. And we use a power meter in order to measure the power transmission of the commodity hardware. And also we use two thermal cameras, one over a RAM and one over a CPU. And we analyze the situation of the temperature on them. And we saw that these are the other details of using the switch and Ethernet in order to analyze these information. And here is the testbed hardware we use in this first type result. And here are the software, let's call it software code, in order to obtain the hardware power consumption and the CPU temperature from the system. So in the first result, I just want to say before starting the plots to you that we have a lot of plots. I just try to select some of them in order to show and give idea about the general scope of the problem. And if you're interested in more information about the work, you can go toward on the details of this kind of papers, which are written, the titles, and the details are, you can access through the information that is will appear at the end of your slide, at the bottom of your slide. In the first figure, you can see about the changing of the active mode to passive mode. In this slide, you can see that the CPU, the server power, when it was in active mode, it will appear in this shape. After that, when it goes to the sleep mode, it's obvious that the power consumption immediately goes to 0. But you will see that the CPU temperature cannot go immediately to 0. It tries to decrease in such a way to reach to the steady state. It means that try to spread out the temperature to the other components in the system. And here the ambient temperature is the temperature of the room that we are testing. For the next plot, we also test the system for different load. we give different tasks, different process to the system. You will see that by increasing the process of the system, it's expected for all of us, the power will increase, and the temperature for the CPU will increase. This slide is talking about the time that we turn the CPU off in sleep mode. So you will see that each 10 minutes we use a camera in order to record the scope of the situation. This is running over CPU. And we will test the CPU in 4 different spots. So due to the sake of the time, I don't explain about the spots, why we select this spot and how we select this one. So in order to get more information, I just advise you to go toward the paper to know more about the details of the selection of that one. And you will see that I want to show in these 2 plots that this is over the RAM. You will see that by increasing the time that device is in a sleep mode, the heat could be distributed over the other component inside the motherboard. So by considering this point, we try to propose a metric in order to control the device. So far, it's a normal case happening in the system. So we would like to propose a parameter which is called accelerator factor. We use this kind of parameter in order to analyze the system and try to, let's call it, to give us more information to the monitoring devices to understand that when and how we could change the state of that device that we are targeting. In order to care about that one, we try to use an accelerator factor, which is combination of the changing of the frequency of that device based on the interface case for 2 states. One, it's in the state number 1, goes to the state number 2, and one, it's back from the state number 2 and come back to the state number 1, plus the transition time or transition duration it takes to cover in this, to be in each of these states. So we just want to highlight that accelerator factor, it's calculated for it could be calculated for a long run, not for 10 minutes, for 20 minutes, for 1 day, assume for 1 day, or for more than that that cases. So that, as you can see, we test the system by considering this parameter, and you will see the result of accelerator factor in these vertical values. And I just want to highlight that if we try to keep the accelerator factor less than 5 in 1 day, we could guarantee that less than 20 transition on that specific server, it costs to keep the temperature of that device less than 20 centigrade. The rate that it could be, let's call it a balance rate and assurance rate for us to keep that device for the long time. By considering this point, we go to the second solved problem, which our aim, which is coming from the transaction paper, which our aim is going to address the lifetime of the general scale problem. In this scale problem, we don't address just one commodity hardware. We have a group of commodity hardwares. It could be different servers inside the network, or just different ISP network inside the network. So each of them, they communicate to each other. So we have a graph of communication of the commodity hardwares. And our aim is to minimize the average accelerator factor over this network. So I skipped the mathematical solution. I just want to give you the general scope of the idea. So we just give a set of the commodity hardware, switch the system, the connection, and the various traffic. So it could be worked with different shape of the distribution of the traffic in the system. We also test it. You can see in the next slide. And it could be based on the limitation of the network. So you know that each link between the 2 commodities hardware that you're communicating to each other inside the network, they have a link utilization, maximum link utilization that they could tolerate. So we also consider these boundaries for each time slot. I just want to highlight that we try to resolve the problem online. You know, this concept is good for the guys that they work in an analytical aspect. It means that we just want to address the problem exactly in this time slot we are discussing now. We don't talk about in the long run. So we would like to address the system slot per slot. After that, we would like to calculate the result per slot and the outcome of this slot would be some time, it could depend on the problem, could be as an input parameter for the next slide. The same as the multiple iteration that you calculate in your machine learning. And we test this result with two different, let's call it in this paper, with two different shape of the network for a flatted tree and that type of the network, and these are the criteria and the characteristic of the network. And in order to speed up the process, we propose a suboptimal solution, which is, we call it AFA, and compare the solution between each other, that one and the optimal solution, with different sub-scenarios. And we have these results, as you can see, that even our heuristic tries to reach to the average accelerator factor, which is the optimum of our solution. For the next slide, which we would like to address, that you will see that our heuristics approach compute the result much lower than the optimal solution. So it gives us an idea that we can apply these techniques, especially the heuristic of this one, in the long scale, in the long run, and the long, the number of huge number of the commodity hardware engaged in the network. And here are the other cases for the various hardware parameters. We tested other, so these parameters are, all of them are described, that these values coming from which, let's call it, which data set and which real devices. So I try to ignore about this kind of explanation. So let's go to the problem number 2. So far we understand about the commodity hardware, different states that affect on the side effect of the network, and the changing of the state of the commodity hardware could be managed, could be controlled, and this is one of the points for the attackers in order to get decision and try to use it for themselves. By considering this point, we go to talk about the mutual costs that happen in the cloud data center. We would like to talk about, we would like to address this case, that the cloud data center could be another type of commodity hardware, which is comprised of a set of commodity hardware, set of servers. In order to talk about the problem number 2, I just want to recall some of the, let's say, general concept that you know. The data center is intensively widespread all over the world, so doing a lot of applications. You can process a lot of applications, a lot of tasks. You can do streaming over this kind of devices inside the network, and it could be used in cloud storage. As you know, data center is one of the commodity hardware, so it could be in active mode or passive mode. And also it could be in active or a sleep mode in our situations in order to reduce the energy consumption and the electricity usage. I just want to give you about just the prolific background of this kind of work is the originate work coming from my PhD 2 years ago, but this work is completely emerged in this year. And we would like to talk about the transition between the active mode and the sleep mode in a long-term period over a system. I just want to say that each server inside the cloud data center could be in active mode or sleep mode. We would like to see the situation over a cloud data center, a huge amount of the servers in the system we have, and each server could change the states. But we should note that we would like to see about money. How much money content providers or data center providers should spend in order to take care of this parameter, in order to take care of the accelerator factor of their servers. So they would like to know that until, let's call it, until how many transition, how many period they can keep this server working. Otherwise they can change it. So this provides for them a cost. It calls it maintenance cost. So maintenance cost caused by increasing the failure rate inside a system. So each server could consume a failure rate, and by increasing the failure rate, it increases the cost of changing that device, the cost of maintenance cost. The second problem that the content provider and the data center providers are engaging with is consuming less energy for their device in order to provide a green situation and so on. So let's simplify our model in this problem as this plot. We have different physical servers in the, physical servers in here, and each physical server using a hypervisor over each physical server in order to communicate with different virtual machine and running different virtual machine inside the system. So this is the general concept of the center, you know very well. And you will see that the group of the physical server could connected with the switch, and the first layer switch and the second layer switch, and it could be considered in each pod, and the group of the pod could communicate with a data center network core switch, and all of them could be connected with a network manager component, which task is to manage the whole situation, manage the whole services coming to the data centers. For example, it could be considered as a software-defined switch, it could be considered as other type of the switch, or normal switch. So the network manager's task is to control the services coming to the system in order to span it, in order to split it to the available pods in the available physical servers and virtual machines running in the system. So in order to propose this kind of techniques, network managers should use some algorithms, some solutions, some ways, some techniques, some methods, that all of them are considered in allocation manager. In this problem, we address the proposed joint solution that it could provide a load balancing and a scheduling of the virtual machines that they can run in physical servers in such a way to decrease the energy consumption of these devices and decrease the number of the migration that this virtual machine, for example, from this physical server wants to migrate in that period of time to the other physical server, whether in this pod or other pod in the system. So we have different energy consumption, different parameters considered in one type of the problem. And the second part of the problem is the problem of each physical server. How many times they can be changed their modes, as I explained in the previous problem. So these are a joint problem, is a nonlinear problem. But I just want to give you a general scope of the descriptive outcome of our formulation. So we propose an optimal maintenance and electricity cost solution, we call it OMEC, which our target is to minimize per slot the maintenance cost and electricity cost. Which electricity cost comprise of three parts: the cost of computation of each request inside each physical server, the cost of migration, minimizing the cost of migration of the virtual machine from current physical server to other physical server, whether it could be in one pod or other pods, and the communication cost between these two virtual machines. Respect to some of the boundaries we have in our system, the capacity, maximum capacity of CPU, how many virtual machines it could be received. This is one of the boundary we have. How much memory do we have in order to we can reside different virtual machine on it. These are some of the limitations that I described this kind of situation in this slide in order to get more information about a solution of each of them and the detail of the mathematical outcome. I advise you to go to visit this kind of paper. And I just want to show some of the slides in a specific case that, for example, in this problem, in this plot, we have 5 servers, 15 virtual machines, and 1 year run. So we have 1 year time slots. So each time slot is it's completely extracted from the reality, the data, and we test the situation over cloud center for 1 year run. Each time slot is around 15 minutes, so we have 35,040 slots that we test the system, and these are the outcomes. So what OMEC said, OMEC is our approach, and these two our approach are the basic approach are available in the environment. We will see that majority of the events, majority of the slots in our solution compared to the other ones consume use less migration. It means that we try to not only keep the maintenance low, but also we try to decrease the number of the migration between a changing virtual machine from one physical server to other physical server. The next plots are talking about the various parameters. So, okay, here is the same, let's call the same test that we discussed about 5 servers and 15 virtual machines. And you will see about accelerator factor and the cost that it caused by accelerator factor. You will see the different situation in our outcomes, in our result compared to the other solutions. And in this plot, we will see the changing of the electricity cost and compared to the maintenance cost and the total cost with various cases that is illustrated with various shape of the networks. So let's back to the last problem, which we are going to address the software, the service function chaining. So these are some of them that I just want to give you general scope, a general idea about the service function chaining. So the guys that are working on software-defined networking and the network function virtualization, they know this concept very well. So I just want to give it very fast about the definition of some of them. So you know the software-defined networking is one of the powerful infrastructure right now is working in the recent network environment. And the service function chaining is the chain of the network function, a group of the requests that it could be served per flow in the system is one of the critical points that right now Cisco, Google are targeting in. So we would like to go first on the system architecture of our model, which is coming from this paper. It's available in archive right now. You can review in this transaction paper. And the scope is this one, that we have a centralized software-defined controller. So it's clear so far. We have a southbound, they have communicating, that means that there are different software-defined switches. Each server are incorporated with each software-defined switch. So we consider these two all together in one node in our problem. And the software-defined controller could adaptively program different flow by using open flow inside each kind of the switch. Our target, our aim that we address in this problem is to propose two components inside the centralized software-defined controller to routing and rerouting the flows from one software-defined switch to their destinations. It could be whatever, any places. It means that each server or each user that connects to the server wants to do a specific task. It should make a flow from the source to the destination which is targeting for. But first of all, it should ask from the central controller from the and give the permission to this kind of device in order to find the destination and find the path for that one. This flow could be a normal flow, which is currently available, or a group of the flow, a group of the action it should be answered. It means that. Just to give you a very simple example. For example, we are one of the users. I'm here. I would like to access IDS and then firewall and then other services inside the system. So I send a request to this server. The server sends a request to the switch. The switch tries to ask the software-defined controller, should I give him permission? We assume that all of them are set. And the software-defined controller, by using a dynamic programming, they give the information to the software-defined switch that, okay, based on the follow table that it has, you say that this guy needs IDS, first of all, he should visit an IDS. We should visit a node that it has IDS service, and then it needs to visit the nodes that it has the firewall. According to the routing or the routing table which the software-defined controller it has, it gives that, okay, so the IDS is over here and the IDS is over here. But the firewall are not residing here, it's in here. So there are just one way to reach to this destination. It means that the server number one should send a request, make a flow, or make a virtual network functions, and send a request to server number two and server number 2 should be visited, and then server number 3 should be visited. So it's a kind of flows that these flows specifically should pass from a specific destination. This is a current problem that they're engaging. So far it's routine, it's not a problem. Assume that there is a failure here. We lose this node. What should we do? And who knows it? The software-defined controller knows this kind of situation. And the software-defined controller should find a path, other paths, available paths in the system, to give the request a response or request of this user. So, of course, in this shape, we don't have the other paths in order to go, but we are discussing about a huge network, a huge sophisticated network. So we call this one a rerouting. So we know the situation happening in the system, and we want to reroute the request from the source to the destination by using the other paths. So these are two different solutions, two different components are engaged in our problem, in our model. The first one, which is a common routing algorithm, we propose common routing algorithms in order to route the normalized situation. And the second one, if we have a failure, if we have a congestion in the network, we should use a rerouting solution. The rerouting solution that it's really clear from your mind is that we have to find the other way to reach that kind of destination. But we should take care about the SFC, take care about the set of the function we have to take into account. So by this kind of concept, we propose some solutions. So we propose some. So first of all, this result is tested over a simulation, and now our team in CNIT is working on a practical one in a small, let's call it small testbed, and then goes to the larger scale cases. Before I say question, I say this one. So and then we would like to. So our aim in this specific, let's call it paper, our aim is to minimize the total energy consumption of the servers, respecting to the maintenance cost we have. So here is an optimal network reconfiguration problem that we are targeting minimize the energy consumption of the servers for each time slot we have. And here are the constraints, follow conservation constraints, server utilization, and virtual network function and service function chaining constraints. We test the system, we test the solution in this hardware. In order to speed up the process, also we propose some heuristics to reach to the suboptimal cases with a very, very fast convergence. So we tested the systems in abelian network topology, which is one of the trusted topology we can care about our system, our model, and test our model over it. So there are 11 switch and 11 server software-defined switch are residing in the system, and we test on over this kind of network our solution. So you can see that in the plots, so our approach is ONR, our heuristic is here. You will see that average path length in our heuristic is much less than that one. So it's really, really appealing from huge case. It means that we can find a solution not only faster, but also try to use less or try to consume less channel in each link in order to keep it again available for the rest of the flows in the system. I just want to highlight that we test the system over 10,000 flows, 10,000 different shape of the flows. And here are the link utilizations and server utilization of the outcome for different runs and different scenarios we have. And let's conclude our discussion. So as you know, for the problem number 1, we have performed a measurement campaign over a community hardware server to take care about a temperature. And we would like to see about the situation. We propose accelerator factor in order to control the state of the community hardware inside the system. And in the larger scale, we show that the lifetime, it could be various in the time, but the different accelerator factor, it could be managed over for each community hardware switch. For the second problem, we take into account the community hardware jointly maintenance cost and electricity cost. We propose the optimal solution, and we test it in the system, and also we address the CPU processing, transfer data, and virtual machine migration. And the last problem which recently I discussed, talking about the SSC over a software-defined network switch in order to reduce the overall energy consumption. So the problem is integer linear programming. We try to solve it in a normal scale, and but for the larger scale, we decided to use heuristics, and we take into account different quality of services, power consumption, average path length, and link and server utilization. For the future direction, let's call it our group CNIT, right now propose some proposal for the European project, and which target for the much sophisticated scale of this kind of problems. And we also can take care of multidiscipline security issues in this problem. So you can assume that we can think about using blockchain in the second problem. We assume that we have geographical cloud data centers in different places. And what is our aim? Our aim is to decrease the money, less spend money. So we have to use a distributed open ledger in order to control that disciplines from the economical point of view of the point of the broker that they're using, that they're serving the request over each cloud data center. This is one of the topics that right now Cisco and Google are working on them and proposing some solution by such as segmentations over software-defined networking, how to manage SFC over segmentation in software-defined network. This is the thing that we are now working on it. And so I need your suggestion for the last point. Any other suggestion you have in your mind, I will be really appreciated. And thank you very much for listening. And some of our emulations, some of our results of our source code are available in our project, which is coming from Superfluidity project. And so these are the references that I taught. And I will be happy if you have any question. Most welcome.
Thank you very much. I'm sure we have a lot of questions. Hassan, you have questions?
Regarding that, what you were said about the future blockchain and you were trying to build out. So what would be the aspect regarding the elasticity and the computational effect and it's not a question, just I want to...
Yes, right now, so this is coming to my mind because as far as I know, right now my colleague Claudio Pizzi is working on it, that we are thinking about how we could integrate, especially the last problem, or maybe the second problem, the closed center, you saw it, in a geographical environment. So we have, for example, the closed center in here, one in Germany, one in other places, okay? So we would like to think about proposing a, let's call it a distributed solution.
You use the word blockchain.
Yeah, exactly.
I was I was thinking about like what you have in your mind regarding the elasticity of the blockchain and the computational effect.
Not exactly. We would like to apply blockchain. Let's call it like this. We would like to use, as far as I know, because I'm not a security man, so of course you're better than me. I just want to give the idea about it. That the blockchain. So let's call it. We are going to use a distributed open ledger, different environment, and we would like to use different sessions. So each session between two cloud centers, two different places, could cost. Why? And why it could be a cost of that one? Because if each session is coming from the traffic coming to the centers. So I'm a cloud center provider. Okay. If I receive this traffic, does it affect on my money, on my pocket or not? And the money I will receive from this traffic, it could be, let's call it benefit for me or not, based on the problem which I have in my cloud center, for the energy consumption, for something like that, okay? So these are like a game. So the traffic comes to the system. So there are different cloud data centers, different places. So there should be a broker or there should be a distributed policy in order to see this traffic could be managed by the cloud data center number 1 or number 2 or number 3 or number 4. So these are the game theory competitions. So one of them, they catch the point, so all of them, let's say, the state table of all of them will be updated, but one of them will be benefit of that kind of situation, the closed center. So these are the, let's say, general concept of the distributed open ledger, but in a blockchain situation. So we would like to think about, not we, I mean the Cisco is working on it. But Cisco is working to proposing a solution, proposing a framework, let's call it like this, to use this technology, the blockchain technology, inside the closed center because of money.
Yeah, it's a question related to problem number 3.
Okay.
Which is like service function chaining over SDN. So I am working on a similar problem. I mean, I'm trying to figure out how to do it. But you talked about, let's say, in your simulation or in your experiments, did you consider the case when SFC has already been set and a failure happens after everything has been computed? Or
nice question.
Okay. Or you, I mean, just consider the case when there could be a probability of failure and then you already, I mean, decided the alternative path.
Nice question. We propose a probability.
Okay.
We propose a probability, so we don't assume that, okay, now we have a problem. No, we assume the system is working. Even the probability of the probable case happening by failure in each kind of switch, we can even handle it in online situations.
Okay.
It doesn't mean that the system now is failure, we will take you out, because we address these two problems all together, jointly. So it means that when the request, so we assume that, first of all, you should assume that, you should consider that the network situation is set. Okay? So the system is okay. It's running. But inside the running, even if the failure happens with any probability, okay, we're working, here is say bye-bye, here say bye-bye, and this time it's lost. So what should I do? I cannot route it because the routing, we miss this destination. So we have two choices. One, we should drop some of the flows because the destination is say bye-bye. So, or we should reroute and using some other way to reach the destination if the destination is available.
Okay.
Okay.
Can I mean, just one more question.
Mm-hmm.
Let's say how do you identify a failure has already occurred? Like.
Yes, because it's a random case, at least for the simulation. Okay, for the simulation point of view, it is random. For example, we said that for the random case in this time slot, for this 11 switch from that in the topology. For that 11 switch, okay, switch number 4 in 80% is done, is the failure, goes to the failure, okay? So these are the probability in each time slot we added in the system. Of course, it could be even managed. We didn't manage this one. Our target was to, let's call it, to routing and rerouting the process. We don't think about, it's a really nice question. I also have in my mind, I have to talk with my team, to specifically, how can we tune that kind of failure? We assume it's random, just this in the simulation. Even in the reality now we are testing, we are, let's say my team, the practical guys are working on in a random case that it happens. Doesn't mean that I should target exactly this one. It's a really nice question.
Because this has not
even
been
for the attack, you can target that one. So we didn't let's call it address that one, but it's really of interest that we can work on it.
Because this has not been, I mean, nobody says in any paper so far I have read, like failure at a particular node, and then what will happen, or will it be just downtime until the system recognizes it?
Yes, it depends on the situation of the system, and in our solution, we target it as a random, and it's nice. We can think about other cases that you have in your mind.
Sure. Thanks.
There's a question from the streaming from Mohammad from University of Rome Tor Vergata, and he asked if there is any way for an attacker to change the hardware state of a node, I presume.
Well, from the I mean, you're talking about the last problem, maybe, or no, general scale question.
He doesn't specify.
Oh, okay. So, yes, of course. So when the attackers come to attack any devices, so honestly, these problems that we address in this slide, we didn't target specifically about the attack types. We just talk about the different problems and different possible attacks may happening on each of the kind of the problems. So of course, the response to the question, it could be definitely the attack could affect on the hardware, so, and we didn't, let's say, anticipate it in these models.
Thanks.
Thank you. Other questions? Okay, and let's thank the speaker. This also concludes the workshop, so thank you all for attending. It was a nice interaction. See you in the next chance.